All right. I think we slowly begin. Welcome, everyone, to this last distinguished lecture of this semester. We're doing this on a Friday, unusually, because there was difficulty for our guests to get here yesterday. So it's my pleasure to welcome Professor Nader Engheta from University of Pennsylvania. Nader is very well known to many of you working in different areas of optical sciences for a number of pioneering works that he's done at least over the past 20 years, particularly interfacing with the kind of thing that I've been doing and the kind of thing that we're doing at the Institute. So Nader is also a fellow Iranian who was, he did his undergraduate at the University of Tehran in electrical engineering, and then left Iran in the summer of 1978. I remember 1978 as a year of World Cup where Argentina won. So these are kind of like, I was 12 then, so these are the things that were important to me. But Nader had other things on his mind. He went to Caltech to do his graduate work. And after his PhD, he stayed at Caltech for some time doing a postdoc, and then joined a company in California as an engineer. And then he joined the faculty at the University of Pennsylvania, moved up the ranks, starting as an assistant professor, and has been a full professor on an endowed chair for the past 20 years or so. So he has won many prizes. We usually don't mention them because there are just so many of them, but there are a couple of them that are really quite impressive. The most recent one, or one of the most recent ones, is the Benjamin Franklin Award. And some of the people who've won that are Nikola Tesla and Thomas Edison. So it's a real honor to get this award, and we're all very proud of Professor Engheta for also having joined this impressive list. He's also a winner of the Max Born Prize of the Optical Society and many, many other distinguished awards. I'm going to stop here and let you give your talk. Welcome.
Thank you very much, David. Thank you. And so in my group, we are interested in various aspects of wave physics. And by wave, I'm particularly meaning electromagnetic and optical waves. And what we are doing is to explore how we can manipulate the waves in a very interesting way to have unusual functionality. And in order to do that, we use metamaterials, engineered materials that have unusual properties. And in my group right now, we have, let me just add this one. We have several projects, some of which are listed over here. And these can be categorized into three main thrusts. Of course, there's no time to go through all of them. I'm going to talk about one of those thrusts, and that is the near-zero index optics. But I'm going to show you two slides only, one each of the other two thrusts that we have. One of the areas that we have been working on in several years is the area that we call it metamaterial-based analog computing. And the idea is that how to actually use materials that when you send a wave through them, it would do mathematical operation at the speed of light. We started talking about how we can actually make metamaterial that will give rise to mathematical operation as you send the monochromatic wave through that. We experimentally showed that first in the microwave domain, showing that this gadget can actually solve integral equations, Fredholm integral equation of the second kind. Then we moved it into the nanoscale. We showed that indeed metasurfaces and the nanoscale with the visible light can actually solve equation with these structures. Recently, we moved this topic into the silicon photonics in order to make it mass producible in the aspects of silicon photonic technology. And most recently, literally about 6 weeks ago, we had another chip made, and this chip can do wavelet transform, at the scale of about 220 nanometer thickness. And we are actually finished the measurement, and manuscript is in preparation. So that's one category of the works that we do. Another category is the area that we call it four-dimensional metamaterials. And these are the materials that as you send a wave through them, not only they could be function of space, in other words, three-dimensional in homogeneity in space, but also they can change in time. And they can change in time very rapidly, and that would give rise to interesting set of physics of the wave. And there are several projects that we have been working on in the interest of time. I don't go through this, but I'm available whole day. If any one of you would be interested, I'd be happy to talk about these other two areas. But the topic of today is this near-zero index optics. What do we mean by that? How did we actually come up with this idea, and what was the motivation? So let's start first with the motivations. We all love Maxwell's equations. And if we write Maxwell's equation in time harmonic sense, source-free Maxwell's equation that you're all familiar with, we know, we teach our undergraduate student, first course in electromagnetics, that if the frequency of the wave is 0, DC scenario, electricity and magnetism are decoupled. But let's ask ourselves this question. Is it possible to make a metamaterial in which that when you have a wave into it, you could still decouple electricity and magnetism as observed from outside observer, even though your frequency would not be 0? Is that possible? Well, the answer actually is right in front of you. Because if we can make a material in which permittivity would be near 0 at the frequency of operation, permeability would be 0 at the frequency of operation, this system would also be decoupled as observed from outside. So that is a crazy question to ask. In the middle of my talk, you're going to see that actually we did that. We actually do the experiment on this, which we're going to see. So that's what we call it, in a very interesting way, this type of structure would give you a field distribution that from this spatial distribution looks like static field. But from temporal point of view, they're dynamics, and they're changing with time. And the reason behind that, as you will see, is that if any one of these two parameters would be near 0, the relative parameters, then in that case, the index of refraction would be near 0. That means the phase velocity is very large. That means the wavelength at that frequency of operation is stretched. And when the wavelength is stretched, then the different points in the medium would have similar phase. And that would give rise to quite a series of interesting, wave physics, some of which I'm going to go over that over here. Before I go any further, let's make something very, very clear. We all know that it is possible to have phase velocity very, very high. But of course, the group velocity, the signal velocity, and the energy velocity obviously is less than velocity of light. And that means these materials must be dispersive. In other words, the index of refraction has to be function of frequency, and around the frequency of interest, you design this material in which n become near 0. But of course, if you change the frequency, that would be different and would not be 0. The question is, what is the bandwidth of that? What kind of interesting range of frequency would be useful for various applications we had in mind? So obviously, of course, everything is fine, the special theory of relativity and all of those things there. That's what we call this near-zero index optics and low-index photonics. Now, just to give you a little bit of, preview of coming attraction in my talk, let me show you an interesting simulation, computer simulation. Imagine that you have a very, very simple waveguide, parallel plate waveguide, very, very basic waveguide that consists of a metallic layers, metallic surfaces. Inside, let's say, just air, and you have a simplest possible mode propagating through this. Of course, that's a very standard waveguide. But now let's do this. Let's assume I come over here and I cut this waveguide in half, putting it one half over here, another half over there, and then I'm going to connect these two halves with this section, which has a completely arbitrary cross-section over here. The shape is completely arbitrary. The separation is completely arbitrary. This boundary is still PEC, perfect electric conductor, so nothing leaks out. And then let's ask ourselves this question. What kind of material I should put inside this structure such that when the observer sits over here and another observer sits over there, would exactly see the same magnitude and phase as though the observers are sitting over here? Now, before I tell you what the answer is, you might say, well, wouldn't the Fabry-Perot resonator would do the same thing? Yes, but Fabry-Perot would do it for a specific length. If you change that length, you have to have a different frequency. But here, I can have this structure any size I want, any shape I want at the frequency of operation. The answer to this question is, if I can have a material in which the relative permittivity would be near zero and relative permeability would be near zero, this can be achieved. In other words, this entire structure from electromagnetic point of view would be a point. Why? Because inside the structure, wavelength is stretched infinitely long. So let me show you a computer simulation of that. So imagine this mode that's coming over here. This is the magnetic field of that mode. You notice you have this wave propagation with a finite wavelength over here, finite wavelength over here, and here the wavelength is, mathematically, is infinite. Which means you have a wave that actually, oscillating with unison, but the wavelength is very, very long. And this would be the effective electric field of that there. Okay? And you're going to see that, in fact, this happens experimentally, as we'll show you later. One of the interesting features of this structure is that those two waveguides that I split it, they don't even have to be collinear anymore. You can put them in any point you want over here. So it's better than even regular waveguide. You can put it like this, you can put it like this, you can put it like this, and it should work. Okay, so enough of preview of coming abstraction. Let's get actually into the topic. So how did we actually introduce this concept? Let me take you back to about 20 years ago. 20 years ago, we published this paper in PRL that actually started this field of near-zero index optics. So what did we do in this paper? We posed a very simple question. We said, what would happen if I have that parallel plate waveguide that I mentioned to you a few minutes ago, like this, with a perfect electric conductor over here, TEM mode propagating like this, and you have another waveguide over here, similar to that, but you would like to connect this with a very arbitrary connections, completely arbitrary. The only thing that we are assuming in this theory, this was the first theory paper that we had in this topic, is that this structure, still when it connects, is still perfect electric conductor, and this basically air inside of that. And if I send a wave from here, what do you expect to see? You're going to expect to see some reflection, naturally. Because, of course, it's not uniform structure there. But then we ask ourselves this question. It was purely a curiosity-driven question. We didn't have any application in mind at that time. We just asked ourselves this question. What happens if I come over here and fill this region of transition region with a material with relative permittivity near zero? Can I have a very strange wave propagation there? Now, what was I thinking at that time intuitively before even we started solving the problem? We said, okay, if indeed the epsilon is equal to zero, index of refraction would be near zero, wavelength would be stretched, so this point has the same phase as that point. So in that case, I would have a propagation over here, and by conservation of energy, I have to have less reflection. But at the same time, there was another intuitive thought that I had that would be kind of counterintuitive to this one. Because when epsilon is near zero, the intrinsic impedance of the wave in that material, square root of mu over epsilon, would be infinitely high. So in that case, we may have a very high impedance mismatch at this boundary. So we may have a complete reflection, in which case, maybe there is no field inside, even though magnitude zero, but the phase is uniform. What good does it do? So these two thoughts were in my head, and then we decided to actually attack this problem. Yes, please. Exactly. That's exactly what we were thinking about. That, maybe that should not work. Maybe that intuition doesn't work. So we decided to solve this problem just to see really what happens other than the intuition. So we decided to solve this problem theoretically, and we got lucky. Because we were able to solve this problem analytically exactly for this case. Now, before I tell you what the result is, let me tell you the assumption we made. We made assumption that this structure is completely two-dimensional. In other words, everything is independent of this axis, just to make the mathematics simple. We assume that this boundary is PEC, so nothing leaks out from that. And we assume that this would be TEM mode, the simplest possible mode that we have there. Then we solve the problem, and this is the reflection coefficient of this mode that's coming over here. So let's walk through this simple formula and see what happens to the numerator if I want that numerator to be 0. So the numerator has a real part and imaginary part over here. If I want the numerator to be 0, I have to make sure the real part is 0, which means this A1 should be equal to A2. Okay, that's fine. The two waveguides should have the same height. But then I have to make this imaginary part equal to 0, 2. But that's multiplication of 3 quantities. If I make any one of them 0, I would achieve that. The first one is K0, which is omega over C. So that means if I make the frequency 0, that reflection coefficient would be 0. But that's not interesting. That's just a DC. That means if I come over here, put the battery over here, I see the same voltage there. Not interesting. Or I have to make mu sub r equal to 0. But mu sub r is effective permeability of this region. So if I make that one equal to 0, then effectively I have a match. But 20 years ago, we were not interested in that because making epsilon 0 was hard enough. We didn't want to make mu also 0, but now we are doing it. But then we had only one other choice, A sub d. But I haven't told you what A sub d is yet. A sub d is the cross-sectional area that you see over here. And that was actually counterintuitive for us. What does that mean? That means if I keep A1 and A2 fixed, and I make this region narrower and narrower to make sure that cross-sectional A sub d becomes smaller and smaller, the wave actually tunneled through this better. And that's exactly the point you were mentioning it over here. So it was very counterintuitive. Why is that possible? If I make that waveguide very, very narrow, actually reflection coefficient becomes less. Things will go through. At first, we didn't believe this. We double-checked, triple-checked our calculation, and it was completely fine. So I'm going to show you the experiment a little bit later, but let me show you the simulation we did over here. So that was the theory, completely analytical. Simulation, what we did, we decided, oh, one thing, by the way, I forgot to mention. One of the interesting points about this result is the parameters it doesn't depend on. For example, you don't see in this formula anything about this angle. So in other words, the two waveguides could be any relative angle you want. That's one thing. It doesn't say anything about, the shape of this structure. It could be any shape you want as long as the cross-sectional area is very small. Okay, hold on to that. Now we come to this. We decided to put this one. We put a material over here, and we assume this material is a Drude material. And we decided to actually solve this problem numerically and compare it with our analytical result. This transmission coefficient magnitude as a function of normalized frequency. You notice that when the frequency gets close to the plasma frequency of Drude, which means the epsilon would be near 0, transmission coefficient becomes 1. That was consistent with the formula we had there. And when we added loss to the system, still we get the maximum transmission there, albeit, of course, not 1, naturally, because there's some loss there. You notice, by the way, that this dashed curve is also the transmission coefficient when we don't have this one over here. And you notice, of course, we get a maximum there. But that's just the Fabry-Perot things. The interesting point is this peak over here doesn't depend on this length, as long as you make that cross-sectional area very, very small. Good. Okay, so we were convinced that that's the case. Let me show you in simulation just to give you a feel for this. So imagine I have this parallel plate waveguide, and I created a huge dent on this over here, and this is air, and I send a wave over here. When I send a wave over here, of course, you get a complete reflection, and you have a standing wave over here. That's understandable. But now I come over here, and I put this material over here, and I make the epsilon, relative epsilon of the material smaller, smaller, smaller. Let's see what happens. So right now, the epsilon relative is 1, and now I make it 0.5. Still, a very good amount would be reflected, but a very little things actually leaks through that boundary. And then we make it 0.1, more will go through, and we make it very close to 0. almost all of it go through the system. It's a very interesting electromagnetic funnel, so to speak. The wave actually squeezes through this very narrow channel, go to the other side with no reflection, and you will see that inside the phase is uniform. That's indication of index is near zero. So let me compare the two extreme cases that we have there. No material there, is just air. You notice obviously a huge reflection, almost nothing will go through. When you make this thing very close to zero, everything squeezes through that channel and go through the other one. Kind of reminds us of the Bernoulli's law in fluid mechanics. But this happens, by the way, in electromagnetic system. Now, you might say, okay, this is an interesting thing, but do we have a material with permittivity near zero? Yes, actually, we have a good series of classes of material. One of them is transparent conducting oxide, yes, aluminum doped zinc oxide, and gallium doped zinc oxide. This is a collaboration we had with Sasha Boltaseva and Purdue, and she was able to make this, to engineer this TCO material. You notice that the real part of permittivity crossing zero at these wavelengths. Of course, the imaginary part is non-zero, but small enough for some application that could be useful. But still, for some other application, these materials are too lossy. We don't want to use them. The better material is silicon carbide in the mid-IR. At 10.3 micron, the real part of permittivity would be near zero. Imaginary part of permittivity is 0.03. This is a very good material, by the way, for this purpose. And CO2 lasers wavelength is 10.3. So this actually would be a very good match for those applications. In the UV regime, my friend Nikolai Geludev from University of Southampton found some of the topological insulators have this property. Yes, please. Yes, relative permittivity. That's right, but that's actually the permittivity of optical signal through them. And the resonance is due to the photonic structures. That's true. Yeah. So usually silicon carbide is used in the much shorter wavelength, which is a good dielectric. But if you actually operate it at 10.3, you get the ENZ properties, epsilon-near-zero properties. And due to one of the reasons that the loss is low is because it's photonic. It's not plasmonic. So this would be for that. Then you might say, okay, these are nice material, but maybe I'm interested in ENZ material at a wavelength that none of these will work. Then the concept of metamaterial comes into play, and you can actually engineer your own ENZ. For example, that's what we did with the collection of the metallic and dielectric structure with the proper thicknesses. You can actually create metamaterial for which you can have the ENZ at the wavelength of your interest, either in the form of plasmonic wires or in the form of layer structures. And another interesting point for those of you with interest in microwave, if you actually look at the rectangular waveguide in microwave, standard rectangular waveguide, and you operate it at the cutoff frequency of a TE10 mode, you actually get the behavior of epsilon-near-zero, even though there is no material inside that waveguide. So in other words, you use the structural dispersion of the waveguide to achieve that. And that's actually how we did the first experiment. And this, C.T. Chan from Hong Kong University of Science and Technology showed that if you have a photonic crystal designed with the Dirac dispersion, with accidental degeneracy, you actually get the effective index near zero in the optical system, and that would be for the low-loss visible case. And Eric Mazur from Harvard actually used the idea of C.T. Chan and showed that you can do it with integrated photonics as well. So there are a lot of interesting possibilities for this aspect. So the experimental verification that we did, almost 17 years ago, we actually used the waveguide in microwave, and we did that. So we created two waveguide system over here with dielectric in between, and this waveguide system is an empty waveguide, and we designed this such that that middle waveguide would be at the cutoff frequency of TE10 mode, which behaves as ENZ property, even though there's no material there. We use the structural dispersion, and we got it. So this is the structure that we have first experimental demonstration. This is the magnitude, and that's the phase of the transmission coefficient. The red curve is the experimental result, and the blue curve is the simulation of the experimental setup that we have there. And you notice this L, we changed this L, the system, so it's changeable that we have there. And you notice as you choose different L, this peak stayed the same. This is not a Fabry-Perot phenomena. This is actually a phenomena that which we call it supercoupling in ENZ structure. And so that aspect, you notice that here, magnitude is there, and the phase of the transmission coefficient is 0, because index of refraction is near 0 there. So, of course, this is a steady state properties. If I run a pulse through this, of course, is a dispersive and other phenomena happens until it becomes steady state. And I mentioned a few minutes ago that that formula did not have an angular dependence. So in other words, we repeated another set of experiment, but this time we bend the waveguide. And it still works. We bend the waveguide, 180 degrees. We bend the waveguide 90 degrees. Reflection coefficient 0, transmission coefficient magnitude 1, phase 0 through this system. So essentially, I used to like to say this, that if these waveguides, when I bend it, twist it, and so on, no reflection. It kind of reminded me of a piece of wires, cables, that we have over here, that we bend it, it doesn't change the flow of electrons. Here, it doesn't change the flow of electromagnetic energy. No reflection. Even though waveguide is big waveguide, but if you put that structure in between, nothing happens. And these are the result, experimental result for 180 degrees bend, and this is for the 90 degrees bend. You see transmission coefficient peak, reflection coefficient very close to 0, and the phase 0 that we have there. So it's interesting, by the way, that this actually gives you these twisting structures that we have there. And that actually started this whole area of near-zero index optics. And for the remaining of my talk, I'm going to talk about the very interesting different set of properties it has. And I'd be happy to talk the rest of the day, if you're interested in many other aspects of this phenomenon. One of the things we did, by the way, of course, that was the one we did it for microwave, but we wanted to actually do it with optics, using plasmonic material. So this is the theoretical work we did. In this case, we use silver over here, which is lossy, and we wanted to show that even with the lossy scenario, this could work, albeit, of course, transmission coefficient would not be 1, but it has a peak there. And that also looked like it working there, and even you can bend it like this, and still this system works like that. But we said, okay, this is interesting. Could we do other interesting things with this phenomenon other than just twisting it and bending it? So one of the things we wanted to do at the early stage of this development is that this experiment that we did that showed that the wave tunneled through this very nicely with no reflection, there's an interesting feature that caught our attention. This is the simulation I showed you before, and of course we did the experiment that I showed you. You see the wave is coming over here, and if you actually plot the pointing vector bends, go through this and go over here. One of the interesting things you notice is this is the field, electric field that you see over here. Clearly you see electric field is very strong compared to here. And it must be because the pointing vector over here, when you integrate it over here, should become the total energy over here, obviously. So that means the electric field over here is much stronger than here. How much stronger is over here? The ratio of the height. Very simple. So that means what? That means if I can actually make the height smaller and smaller, as long as it's not exactly 0, then I can make the electric field very, very high, and I can make it over the extended length over here. And that's one of the things that in plasmonic field we always love to have. We want to have a hot electric field, but usually, of course, in a very small location. Here, we can have it over extended region. Of course, the volume is still small, I understand, but at least over the extended region. So then we said, this is interesting. First of all, reflection 0. Secondly, electric field very high with basically reasonable amount of power that you send over here. Third, the phase is uniform. What does that give us? So first of all, whenever we see that there is a hot spot, a couple of things come to mind. Can I use it as a sensor? Can I use the nonlinearity there? And we tested both of these. But before I go there, another interesting feature. So if I send a wave over here and have high electric field, what would happen if I put an emitter over here? Do I have good radiation? By reciprocity, I should. So I was really interested to see whether I can put an emitter there. Can I put a quantum dot there? Can I put an optical antenna there? And Vahid, you and I met, the first time we met, we were talking about optical antennas. Remember that? That how can actually I put something there? So one of the things we first did theoretically, So, okay, what would happen if I come and put a dipole there and look at the radiation of that? So if I put a dipole there and you put the radiation of that, you see it looks like the near field of that dipole is stretched. So if the near field of the dipole is stretched, what would happen if I put two of them? Even though their location could be quote-unquote far away, but they can still feel they're in the near field of each other. And doesn't matter where you put them. So here in this theoretical work, we put 9 dipoles over here. We put the 9 dipoles randomly, and we put the 9 dipoles with equidistance. Both of them give the same radiation. Makes sense, because you're stretching the wavelength, so you can put the dipole anything you want. So we were very excited about this possibility, particularly in the context of quantum system. Can I put in quantum emitters there? But how can I put the quantum emitter there? So what happened, by the way, this also the field distribution, you see that stretch, near field stretch. So in one of the conferences that I was giving talk on the theory of this, my good friend Albert Polman, who is in the AMOLF, Institute of Nanophotonics, Amsterdam, came to me during the coffee break. He said, you know, actually I have an equipment in my lab that we can try your theory. So why don't we do that? So I went to his lab for 1 week, and we put our heads together, and we designed a system, and we tested in his lab, and it worked. So what does he have in his lab? Cathodoluminescent spectroscopy that many of you are familiar with. So in that case, electron beam comes over here to sample. It creates photons there. It collects the photon by parabolic mirror, either goes to a spectrometer or with a CCD camera, we can actually map the radiation pattern of this. So I went to his lab for 1 week. We put our heads together, and we designed this waveguide. This is the optical version of that microwave waveguide that we built in my lab, but this was done in Albert's lab. So this is 2 micron length, and inside is SiO2 that you see over here. It's covered with a silver. With focus ion beam, we cut the two ends are open. So this is about 85 nanometer over here, and we created this waveguide, several of them you will see, with a different width. And then we put this waveguide in his cathodoluminescent with the electron beam 30 keV coming down. And what happens is when the electron beam coming down goes through the silver layer, goes to the dielectric in the waveguide. When it gets to the dielectric, at that point it emits transition radiation. That became the optical antenna we were looking for, and we could put it anywhere we want. And the resolution of his beam was 4 nanometer. So you can actually map every 4 nanometer along this. And that's what we did. So this is a simulation of that map that we see over here, and this is the experimental result that we got in Albert's lab over here. What you see over here is that, of course, when the electron beam comes and emits photons, the spectrometer would measure the number of photons as a function of wavelength. And here we are showing that at every one of these pixels you see, that's where the electron beam hits and how many photons we get from there. And then the location will change, and you have this map. This map, of course, is not that surprising because that's a modal structure of the waveguide. But what really was interesting for us, if you look at the top view of that waveguide and this electron beam is coming like this, at the center of this, what would happen if at every point that the electron beam hits, we look at the number of photons as a function of wavelength and as a function of location of the beam. Then you get this map. Vertical axis is the location of the beam that's coming out from 0 to 2 micron. Horizontal is the wavelength of the captured photon, and we see this map. Again, at the moment, that's not surprising because that gives you the map of the modes structure. But this was for a waveguide that the width of that was 250 nanometer. But we had several ones we made. This was a 250 nanometer. This was 240 nanometer. And this was 180 nanometer. You see, when it became 180 nanometers, the emission stops over here. This is the cutoff of that waveguide. And that was the ENZ point. And you see, by the way, that no matter where the electron beam comes, the emission is the same. So that was an experimental proof that indeed that structure at its cutoff behave as ENZ. So regardless of where I put that electron beam, the emission would be the same. Now, of course, you have some hotspot over here, hotspot over there, because that's at the edge of the waveguide. And usually the photon density of state is higher there. But along this, you get the same thing. So here we prove that indeed that structure behaves as ENZ. Later on, Albert and I continue our collaboration. We actually built that system of layered structure, as I mentioned to you, and we tested it, and that also is ENZ as well. So one of the things that I mentioned. Yes, please, Vahid.
Right now, you just brought the concept of waveguide cutoff directly together with ENZ.
Yeah.
But this is just a feature of this. If you just have a waveguide and go to cutoff, you don't get automatically ENZ.
You do. From the point of view, let's say for the TE10 mode, you do get. Why is that? Because at the cutoff of that mode, the wave number along the direction becomes 0. That's a cutoff. And that's exactly what happens in a regular medium with epsilon-near-zero. Because k, omega square root of mu.
Doesn't that make this somewhat trivial that you, no matter what material or whatever, you always go to cutoff and then you get this?
If you have a waveguide that is a closed waveguide, not the optical fiber, that would not work. But it should be a waveguide that walls are not penetrable. You have that one there. In that case, the cutoff of the mode, what happens when the wave number in the direction becomes 0. And that imitates the behavior of the wave in a medium with the epsilon-near-zero.
So is that something that was already known or used in gigahertz or microwave type of?
Yes. Of course, cutoff of that was very well known there. But what we use it over here is to show the experimental proof of concept there. But then later on, we actually use the material itself. And that was the first experimental one that we wanted to do in microwave. Later on, just like this one, by the way, this, of course, there's no waveguide over here. This was just a layered structure. And indeed, you notice that crosses 0. So this doesn't use any waveguide. But that was the first one that we had to do in order to see with it. Because, and of course, later on, we extended. So this one, for example, what we did, we said, OK, if we have a very hot spot extended over this region, can we use it as a sensor? Can we use it as nonlinearity? As a sensor, yes. So in fact, if we have something like this and the wave goes through this, what would happen if I go over here and I change the epsilon of that a little bit? Because the field is very, very strong there, small change of epsilon can actually change the transmission and reflection a lot. That becomes a good sensor. We came up with this idea. It effectively becomes like ENZ-based transistor, like a gain and a drain and source and the gate. But here, the gate is a variation of the epsilon you have over there. And we studied this theoretically. And recently, by the way, we did this experiment with a collaborator in Spain that indeed we showed that you can have this system and you can put the analyte there. And by changing the dielectric constant of the analyte very, very slowly, you can actually detect that. So it becomes a very interesting detection system. Nonlinearity. So obviously, when you have a very high electric field, the first come to mind is that can I use it for nonlinear structure? When we were working on that one, my friend Yuri Kivshar, you're familiar with his work in nonlinear metamaterial, he found out about the work we do. He was very excited. He said, why don't we join forces? We bring nonlinearity into this. So he sent David Powell, at that time was his postdoc, to my group. And we did this experiment, by the way, in my group by using a varactor. And varactor is a nonlinear capacitor that you can actually tune it. We did that in my lab. And indeed, we showed two things. That by changing the capacitance there, effectively you're changing the epsilon, so you can actually tune this as a sensor. And what we showed is that if you actually send the microwave power and you change the power, that actually self-tune itself. So in other words, you can use the microwave power to actually change the permittivity, in this case capacitor, and indeed worked. That concept of nonlinearity of ENZ later on resurrected itself. So 3 groups. My group, in collaboration with Luca Dal Negro, showed that indeed the epsilon-near-zero and thin oxide, indium tin oxide, can have a very enhanced third harmonic generations. Bob Boyd, from University of Ottawa, showed also that the ITO can have a very high nonlinearity, and also Vlad Shalayev, Sasha Boltoseva, and Daniele Faccio, they showed that. So 3 groups independently, we showed that indeed one of the interesting characteristics of ENZ is the very high nonlinearity that we can achieve. Then we said, OK, What other interesting things we can do? So one day I was actually looking at some of the literature, and of course you're all familiar with Meissner effect in superconductivity, that the magnet could be suspended, levitated. And then I said to myself, this is interesting. So of course, obviously this is a quantum mechanical feature with this, and you put a magnet there, of course it would be levitated. And the reason it's levitated because the magnetic field B is expelled, cannot be enter into superconductivity. But from electromagnetic point of view, as observed from outside, that means vector B has to be 0 inside of this. Then I said, do we have an equivalent of that in E and Z? If I have a substrate that have epsilon-near-zero, that means vector D in Maxwell's equation should be equal to 0. So that means vector D has to be expelled. So I said, what would happen if I put an electric dipole over here instead of magnet, put an electric dipole, and I oscillate this electric dipole at the frequency for which the substrate becomes E and Z? Then in that case, vector D cannot penetrate. So would the dipole be levitated over here? Could we have an equivalent of Meissner effect, but for electric dipole? Obviously, of course, the two phenomena are different. This is quantum mechanical, this is classical, number one. Number two, this can happen at the static magnet. This has to be dynamic. I cannot have epsilon-near-zero at the static limit. It has to be dynamic. So what if, for example, I have a dipole over here that do that? So we studied this. We studied this, and we found that the situation is better than we thought. Because we thought that, okay, if I have a dipole on top of this, I would get a levitation if epsilon is 0. But we found that actually is better than that. It doesn't have to be 0. Any permittivity between -1 and +1 would allow that dipole to be levitated, even in the presence of loss. So this theoretical plot that we have over here, this is the epsilon of the substrate, the real part. This is height of the dipole that we put over here. The red color would show the repulsive force. The blue color would show the attractive force. So you notice when the epsilon is between -1 and +1, there's a repulsive force, a levitation. We added loss to that, still the phenomena is there. And the reason the phenomena is still there, because this is a very low Q system. We don't need to have resonance over here, essentially. So when this theoretical paper came out, there was a lot of interest. One of my, pair of my good friend, Pino Estrangi from Case Western Reserve University, and Onofrio Marago from Messina Center in Italy, they got very interested in that and said, well, let's join forces and try to actually show this experimentally. Because if we can show this experimentally, that means I can have these nanoparticles, levitated from the surface. So in that case, I can move them without friction. And that could have an interesting application in medical system. So we joined forces, and the idea is that if I have a particle and I'm using the optical tweezer, I can actually hold the particle there, and then I send another laser signal with different wavelength at which I create a dipole moment on this particle at the frequency of E and Z. Would this one go up or down? Onofrio is expert in optical tweezing, so this is happening in his lab. This is work in progress. We extended our first theoretical work to much more general case of particles, not necessarily very small. And this is still theoretical work that we study all possible combination of the layered structure and so on. And this is actually an experimental result that Onofrio had got from his lab. We haven't published this yet. We are still working on interpreting some of the results there, but indication is that we are in the right direction. There are things we need to understand from this experimental result, because part of this could be thermal effect, part of this could be possible Meissner-like effect. We don't know that yet, but the fact of the matter that the experiment shows that the substrate E and Z, we get a different feature than the substrate is silver or glass. So this is work in progress. Hopefully, we're going to submit this soon. We'll see. What are we doing with time? Okay. Photonic doping. So let me change the subject a little bit. So we said, okay, this material has interesting properties. And then we said, okay, in electronics, we know that if I have a pure intrinsic semiconductor, which has certain electric property, like silicon, for example, and we know, by the way, that if I put the donor atom there, the doped silicon, either donor or acceptor, Then you can change, by the way, the electrical and optical property, and this, of course, foundation behind semiconductor industry. We know that. So we ask ourselves this question, could we have something like this, by the way, for ENZ material, or for optical system in general? In other words, if I start with a pure photonic material, can I put an external object there and change the optical properties completely? The answer is yes, of course. People in photonic crystal have done that for years. If I have a photonic crystal over here, as you all know, and you have a band gap, and you put a defect there, of course, you create the channels of that. But then we wanted to actually see that for ENZ. So imagine that I have an ENZ material over here completely. Has certain properties that we have talked about so far. But imagine I come and I put a dielectric particle there. And for now, let me assume one dielectric particle. That would change the scattering property of this. But how much it would change the scattering property? In what aspect it would change the scattering property? At first, you might say, what's a big deal? If I have any material and I put a dielectric, it will change. But you will see actually with the host of ENZ, the change is a very, very unusual change. So let me walk you through that. First, imagine that I have the block of this ENZ material that is long in this direction, just to make our life easier. And the epsilon is 0, and this is non-magnetic, so mu is 1. And I send a wave over here with the magnetic field parallel with this. Okay, not a big deal. You get the scattered field, you have everything there. It turns out, by the way, if you go back to Maxwell's equation and I assume epsilon 0, the curl of H equal to 0, and here H has only one component in this direction. So that makes the life a little bit easier. I only have one component, and I can find the electric field from this simple formula from Maxwell's equation. But you notice something interesting here. You notice that obviously, in order for electric field to be finite, because the epsilon in the denominator of that can be very close to 0, that means the gradient of magnetic field should be 0, which means the magnetic field over here is uniform, regardless of the cross-sectional shape of this. In some sense, that's not surprising because the wavelength was infinite anyway. So can we take advantage of that? Can we take advantage of the fact that regardless of cross-sectional shape, my magnetic field is uniform there? So let's do this. So let's assume I come over here and I put this dielectric rod over here with the epsilon of that, call it epsilon p, and that's just regular epsilon. Epsilon of this yellow region is 0, incident wave coming like this. And imagine that you go outside and sit outside and look at the scattered field. Based on the scattered field that you see, can you guess what is the effective parameters of these structures? Kind of like effective medium theory. It turns out, I don't want to bore you with the detail of the mathematics, it turns out that if you go through all the mathematical analysis, yes, you can actually assign an effective permittivity of this entire structure, which follows this general formula. But it's interesting, by the way, that if you actually put the values over here, you find that the effective epsilon stays at 0. So let me repeat that again. I start with epsilon near 0, I get certain scattering. I put a single dielectric rod, obviously the scattering would be different. But for the outside observer, that scattering still looks like it's coming from epsilon effective 0. Even though you have added some dielectric, but it still looks like it's coming from epsilon 0. But how is that possible, that my scattering is different, but effective epsilon still near 0? What other things have changed? Effective mu. And we calculated that, and we find out the effective mu can be engineered quite nicely. Now, this is interesting. That means I start with the ENZ, which is non-magnetic. I start with the dielectric rod, which is non-magnetic. Just combine these two together, I get an effective magnetic different than 1. And that is this formula. And this formula actually is pretty simple if you think about it. You notice this formula consists of A, which is the cross-sectional area, A sub h, which is cross-sectional area of this host yellow region, Bessel functions of k pi rp, and this is r, the radius of this dielectric, kp is the k of this, and that one. You notice this formula does not say anything about cross-sectional shape. It does not say anything about where I put the dielectric rod. It does not say anything about the relative magnitude of this except the areas like that. And if you plot that effective mu, you get this one. What does that tell us? That I can easily engineer, and I'm going to show you the experiment, I'm going to engineer an effective mu you like to have. You can have effective mu near zero, like here. You can have effective mu very highly positive. You can have effective mu negative for this. So this is actually a good example of metamaterial, that you combine two materials, none of them is magnetic, but the combination would give you magnetic properties. So let's look at some simulation and the experiment. For example, here we choose this radius over here, that would give you effective mu zero. This is the simulation of putting a dipole in front of this, and you see the field distribution everywhere, inside and outside. But now let's do this. Let's assume that you consider the same geometry, but with a hypothetical value of epsilon mu zero. You get this one. I would like you to actually compare the external fields of these two. Identical. Completely identical. Not inside. Inside is different, but outside, identical. So for outside observer, this looks like effective mu near zero. And that has an interesting things with regard to the quantum emitter couplings. I don't have time to talk about this. I'd be happy to talk to you later on that. One of the interesting things that happen is look at the field distribution inside. If I change the location of that dielectric rod inside, it does not affect the outside field. Absolutely nothing. But inside field will be different, which lead us to actually interesting property. What kind of cavities we can have with this? The cavities would be actually interesting cavities that would be independent of the external shape of this. We'll see. So can we actually have a perfect magnetic conductor? Can I have a structure that imitates effective mu very, very high, which we don't have in nature, but we can actually make that? This is, again, comparison. You notice outside field, identical. And so let me jump over this. We did some interesting case study. If you have a window of E and Z and you put a little dielectric rod, by just changing that dielectric rod only, you can actually change the transmission of an entire window. That could have an interesting application we studied, for the structure that you see the wave can go through or the wave can stop only with just changing that dielectric rod only, not the entire screen. Anyway, so cavities. Of course, we all know that cavity resonant frequency depends on the geometry, obviously. But not in this case. So in other words, can I have a cavity resonator whose resonant frequency would be independent of the external shape of the cavity and only locked into E and Z frequency? It's possible. So let me show you this structure. Imagine that you have a three-dimensional cavity, which is open cavity, made of E and Z. And you put a dielectric sphere inside of this. You can put it anywhere you want. It turns out that this crazy geometry has a very interesting electromagnetic mode. This electromagnetic mode, electric field of that, and this is the magnetic field of that. Now, it's very interesting. If you come at the shell and sit over here, you notice that you have electric field non-zero. But there is no counterpart to the magnetic field. That was the decoupling that I was promising you at the beginning of my talk. So you can have a scenario in which you can have electric field non-zero, oscillating with frequency omega, but there is no counterpart to the magnetic field. You go inside this regular dielectric sphere, you see both of them. Naturally, that's a regular dielectric sphere. This interesting cavity has actually stored electromagnetic energy, even though it's open. You add a little bit of loss, of course, starts really radiating away, but in the absolute sense of lossless, this open cavity holds the electromagnetic energy there. So this, you can actually morph the cavity from this one to this shape to this shape. You can have all the variation of one shape to the other, and all of them will give you the same resonant frequency, but different quality factor. This is one of those cases that you actually decouple the resonant frequency of cavity from its Q. And that could have an interesting possibility for quantum optics. We study some aspects of that and to see what happens. We experimentally verified that in the lab. We created 3 different cavities with this shape, with this arbitrary shape, with this arbitrary shape. All these three have the same cross-sectional area. And we put a dielectric rod inside of that. There's one single dielectric rod, but we put it in 3 different locations. So we experimented that 9 different times. And this is the structure, and this is the result. All of those resonant frequency is the single one, regardless of that shape of it, regardless of where I put the dielectric rod. So anyway, I'm going to quickly stop. One of the things we study just for fun, theoretically, is that can this structure really engineer and basically tailor vacuum fluctuations? Indeed, it can, theoretically. Somewhat similar to the photonic bandgap structure. The difference is this, the shape could be anything. There's no periodic structure over here. If I have a blob of this epsilon-mu-near-zero and create an enclave inside of that, I can actually basically control the vacuum fluctuation inside with respect to outside. Anyway, and finally, this has a very interesting thermal effect. And if you actually heat up this object and at a certain temperature, when you have a distribution of all those fluctuating dipoles, at the frequency for which the structure behaves as E and Z, the wavelength is stretched, so the incoherent radiation of thermal become partially spatially coherent. So essentially, you can have a system that kind of approximately behaves as a phased array, but for thermal radiation. So you can actually look at the interesting aspects of thermal radiation of this. Let me show you this. Different structure, different cross-section. These would have different thermal radiation pattern. So you can actually change this structure, even though there's no pattern on them. This is different than Jean-Jacques Greffet's work, that you have pattern structure on silicon carbide that would point thermal radiation direction. This works based on the E and Z structure. And finally, there's a very interesting connection between E and Z media and ideal fluid. So if you look at ideal incompressible fluid, you notice in that fluid, the Poynting vector of the light, curl of S is equal to 0 and curl of and divergence S equal to 0. So if you have the epsilon-mu-near-zero structure versus regular dielectric, you notice in regular dielectric you have these vortices of Poynting vector optical signal. But if you have a medium like this, you never have a vortices there. So that becomes very interesting similarity of E and Z electrodynamics versus, fluid dynamics there. And actually, one of my collaborators, Professor Yuli, who was my postdoc, in his lab, he did actually an experiment, indeed showed that you cannot have the turbulence. In this type of you can have the optical turbulence. One of the crazy ideas that we're looking at is that could we actually use Bernoulli's law over here in electromagnetics, meaning that if I have something like a wing, can I have a lift electromagnetically? Same thing that in fluid do that. That brings me to the end of my talk. I'm going to thank Vahid again for his kind introduction and invitation. And thanks all of you, and I'd be happy to answer any question you have. Thank you.
Thanks very much, Nader, for this beautiful talk. As you mentioned, we got to know each other many years ago as people in nano-optics started to think about what we now call optical antennas. But at the time, the first time that I wanted to write a paper about an optical antenna, I knew that an antenna was something that I'd seen on the roof or a TV, and that's all I knew about an antenna. So we had to go and actually try to understand what's the definition of antenna, and it was very difficult to find out. Of course, antennas were completely well known in electrical engineering, but physicists never really did anything about antennas. So I think over the past 20, 25 years, there's been a very, very fruitful, let's say, bridging from your previous world to optics, and you see that this, as you said, Maxwell's equations are extremely rich, and all the things that we saw in Jackson, every single problem has lots of secrets that you've gotten a lot of insight to. So wonderful. I have a lot of questions, but I think I let people in the audience begin. Yeah. I have a cube as well, but I'll give you... No, there's Zoom.
Great talk, thank you.
Thank you.
The phase in that thin region didn't seem to follow a sign, but it seemed to switch and then stay, or, I mean, I'm not so sure if that was just a color effect, but it seemed that there was some kind of a phase memory or so, I don't know how you want to call it.
Yeah.
Which means that if you do a Fourier decomposition, you would expect higher components.
No, that's interesting. But the fact is that the frequency is a monochromatic. The signal is still monochromatic.
Yeah.
What happens is the wavelength is stretched.
Right.
So if you stand at every point in that channel, narrow channel, you still see the same frequency.
Yeah.
The
Fair
only
enough.
difference is that the person who sits next to you would see the same phase as well. Because phase velocity is very, very high there. Group velocity is slow, by the way. In other words, we did also the transient signal. And transient signal takes a longer time, of course, to get there in order to establish that. But from temporal point of view, is monochromatic. So if you do the Fourier analysis at each point, you get the single frequency. I mean, passing the transient time and things.
Okay, interesting. Yeah. It appeared different to the eye.
It looks different to the eye because the entire thing is uniform. In fact, if I may, let me show you. That's an excellent question, and I think your answer to that will be here at the beginning of my talk. Let me, when I showed you this simulation. This one. See, you notice this field is changing monochromatically, but in unison. Now imagine this happens in that tiny region. That's what your eyes see. But here...
It doesn't
match the same.
Yeah, it's the same thing. One thing, by the way, that...
The very thin one.
Oh, the very thin one is here, okay. Let me see, where is the thin one? Thin one was here. This one. Yeah, no, but that's just because, of course, remember, it's a variation of blue. It's if you look at this, you know, it stays from here and jumps over there. But actually, there is a segment that goes through this. It becomes harder to see over here. If I make this thing narrower, it becomes very similar to the one that you see there. One of the reasons, by the way, in this simulation, we didn't make it too narrow, because otherwise it would be hard to see. Sure.
Other questions?
Oh.
Very nice talk, very clear.
Thank you.
About this case, what is the physical intuition behind the small cross-section of the channel? I mean, is a kind of topological transport, or?
Thank you so much for asking, because I have a slide for that. I'm glad you asked that, because I had that in my talk, but it would have been too long. So let me show you. Very interesting question. It is also topological true, by the way. We have studied the topological aspects of that. That's a whole other thing. Why do this work, by the way? The reason is this: impedance matching. So what happens, you have one waveguide here, another waveguide here, another waveguide here. In order for this to match this one, you have to calculate the impedance of the waveguide, not the intrinsic impedance of the wave. Impedance of the waveguide. So that means voltage divided by current. Voltage is electric field uniform multiplied by height. Current is the magnetic field multiplied by width. That becomes this. If you actually split it, that becomes square root of mu over epsilon h over w. Hold on to that. If I go from this waveguide to that waveguide, I have two impedances that need to be matched. That means this. Now the answer becomes clear. That means epsilon 1 is the epsilon of there. That's just regular air. Epsilon 2 is the epsilon of E and Z. So this denominator is very small. In order for this to become this, H2 has to become small. That's what the height should come down. And that becomes impedance matching. Now, the follow-up question would be this. What would happen if I make mu2 equal to 0? We did that experiment too. I don't have the slide over here. That becomes the opposite. If mu2 becomes small, then I have H2 very high. So you have a waveguide that's coming over here and has to become fat and then coming over here. It would be impedance match. And finally, what happens if both epsilon 2 and mu2 are 0? H2 become arbitrary. And that's the picture I showed at the beginning. Any blob would do it. And it worked.
Other questions? Sorry.
Hey, right there.
So you always showed about the effective permittivity. I just wanted to know more the intuitive picture, how you define this, because in a smaller scale, especially when you have like periodic layer, you have like change in permittivity.
Absolutely. Yeah.
You sort of define the effective permittivity and how the definition matters in this regard.
Excellent question. But so just to make sure I understand your particular point, you're talking about the layered structure, for example. Am I right? The layered structure.
I mean, layer and also the metamaterials, if you have, like, for example, wires, like periodic wires that you have, and then you consider the effective permittivity of the whole thing.
Exactly. First of all, let me make it something very clear. In the case of photonic doping that I mentioned, that I have one column of E and Z, and I put one dielectric rod over there, it's not periodic. It's just only one single dielectric rod.
Yes.
That's actually a very important distinction. In a regular effective medium theory, you have to have periodic structure, you have to have the size small compared to the wavelength, you have to have separation compared to the wavelength, but not with E and Z. That was one of the beautiful aspects of E and Z. You can have a structure, several wavelengths, and one dielectric rod, you can have effective permittivity. That's the beauty of that. And I can explain to you why that is the case. Because if you have E and Z, magnetic field is uniform there. You put one dielectric rod there, doesn't matter where you put it. It sees the same magnetic field. And because magnetic field is uniform, that means the field inside the dielectric should be azimuthally symmetric. Otherwise, it would not match the boundary condition. So for the outside observer goes around this E and Z, it would see the same H. But inside that dielectric, we have more flux of the magnetic field. So for the outside observer, it will see the same H, but with a different flux. That's what you have different mu there. And that works very nicely.
One last thing.
Sure.
I think that would be also interesting to think about, like, I can hide materials inside this because the outside observer doesn't have any clue of this, and you can put sensors or do whatnot in that.
Absolutely right.
Nobody sees it from
Absolutely right. Back in 2005, we did the first cloaking.
Okay.
And that actually came through this analysis. Exactly right. So what we did the experiment of a structure that has scattering, and we put a layer around it, and that layer effectively gives you the epsilon less than 1. And when we give you epsilon less than 1, when the wave enters, go through this faster than the wave goes inside the dielectric, they match together, and the total scattering cross-section came down, and we were able to cloak a system. I'd be happy to send you that paper, 2005, PRE.
All right, we take another couple of questions. Stefan?
So I'm still intrigued by your waveguide here, and I understand the mathematics, but it's still not intuitive. I wonder, you know, this waveguide is much smaller than half of the wavelength.
Much, much smaller than half of the.
But then can this be described as a tunneling effect, because your wavelengths become so long that this is a very, very small tunnel barrier you are effectively building there?
Effectively, yes. Effectively, even though physically this size could be as long, but when you are inside that layer, its wavelength is very long. So basically, phase here and phase here is the same. That's right. That's effectively what happened. That's one of the reasons, by the way, we also studied, I didn't show it over here, that we studied the coupling between two quantum emitters, between this. And if you put the two quantum emitters near each other, that's a decay state that happens. When you put it away with the structure in between, it will have the same coupling. And that's exactly because this structure inside the wavelength is very, very long and brings this together. As I mentioned, this looks like an electromagnetic point over here, even though structure is like that. But one of the interesting points of your question is quite fascinating. And you notice over here as well, you notice that the wave is coming and bend. Before it even gets to that wall, bends. Why is that? Because there are a lot of near field effect over here that modifies your Poynting vector. The Poynting vector is modified, squeezes through that with no reflection. And that actually exactly the mechanism happens there. I'll be happy to talk to you more and show you more result.
Take one more question, and then you have a reception outside. You can still speak with Nader. And I remind you, there was an email, especially for graduate students. There will be an occasion for you to meet with our guest this afternoon if you want to pick his brain a little more.
Sure, I'd be happy to answer any question you have.
Very interesting talk.
Thank you.
So we have the intuition with metamaterial. Okay, you change the filling fraction, like with Garnet, Maxwell-Garnet theory, etc. But then intrigues me this last part where you put just dielectric wire. But I think it's also a lot of the boundary conditions that in far field you have like all the time the same. So if I have, for instance, a gradient index, if I put a wire, and I think it's also a lot of the actual contrast of index.
Okay.
Because it has to be very high refractive index, the dielectric you put, or not?
No, not necessarily. Irregular dielectric. It doesn't have to be high index, high epsilon.
Like unrealistic materials. It can be
it could be silicon.
Okay.
Yeah, that's fine. Yeah.
And then if I have like a medium inside, for instance, but I have a soup of a gradient refractive index, etc. But then I match the exact boundary conditions from the outside. I'm gonna have the same far field, maybe.
Yeah, exactly. So let me show you this. Thank you for the question. That's very interesting. And I'd be happy to talk to you more in detail. But let me go back over here. Here. So let me. This effective medium theory is consistent with the Maxwell-Garnet that you were mentioning it very correctly. This is a general formula, but I would like you to actually walk through this formula to see what happens. Epsilon h is epsilon of the host. Epsilon p is epsilon of the particle. Delta is the volume fraction of that particle. Now, this is a general top things, but there is one interesting exceptional thing about this equation. Look at what is the multiplicative factor over here, epsilon h. That epsilon h kills everything. Doesn't matter what epsilon p is. That is actually one of the characteristics of epsilon-near-zero. Unless this delta become near 1. If delta become near 1, then you notice what happens. Then this goes ahead, and that epsilon h would cancel. So what you would like to have is you would like to have E and Z, and you put a dielectric rod over here. But you don't want this dielectric rod to be almost the same area of E and Z, because there's no E and Z would be left. So other than that, you notice that this will kill it. So epsilon effective would stay near 0. And we were surprised with that as well, because of course the scattering will change. But where does that change can be attributed to effective mu? And that's actually quite fascinating, because that answer to what I mentioned to you, what happens is, actually, let me show you. I actually have a slide for that. I just remember it at the end. Where is it? Here. This is actually the physical explanation of this. You have this E and Z, and you have a magnetic field coming out. You put this dielectric rod over here. Now, magnetic field in this light blue region has to be constant with the space. So what happens if you start walking from here and calculate the magnetic field and the flux, magnetic flux? What you have a magnetic field uniform. Inside this, you have a magnetic field variation, Bessel function variation, and uniform. Now, if you calculate the flux of this, flux of that would be very much depends. What is this one over here? But this side is still the same. So if the observer from outside starts walking around the perimeter of this object, always sees this H. But it would see a different flux inside of this. So from the outside observer, it looks like different mu. And that engineering you can do by the radius of this, how you can bring this thing up and down, effectively making it 0 flux, if you want. And we did actually extension of this work. We created actually an optical transformer, just like what Nikola Tesla did with the regular transformer, that the flux goes through here with this one. You can actually do that in optics. We haven't done the experiment. It would be interesting to talk about the experimental aspect. But yes, you can actually do something that would change, vector D from one system to another system, and you can have an optical transformer. But that's just because the flux, you play around with the flux over here. I'd be happy to talk more. But
all right. There's one question from the Zoom that I forgot to mention.
Sure.
Maybe a quick answer to that. The question is if there's any singularity that appears when you get epsilon-near-zero.
Yes, very good question. Yes. Practically speaking, no. Because, of course, any material, even with the real part of permittivity goes near 0, the imaginary part. mathematically speaking, could be very, very small. So that would prevent, for example, of phase velocity to become infinite and so on. It becomes really finite size. Interesting point is that group velocity could be very small, but actually because of that small amount of loss, group velocity would never become 0. So that's what actually the experiment works, because the energy go from one side to the other.
All right, please join me in thanking Nader for this fantastic talk.
Thank you.